Woot woot, it's 5.6, and this is the culminating section of Chapter 5. We don't learn anything new, we just put everything together in 5.6 to sketch the curve of any given function. And that's pretty crazy. Last year, when you sketched polynomials of high degrees, you thought you were pretty smart. Now, not only, well, polynomials of high degrees are nothing for you now. Now you're able to sketch any incredibly difficult function with incredibly difficult asymptotes, etc. Pretty impressive, grade 12s. Okay, so as we sketch here, we're going to go through these steps. We're going to find the derivative of the function and do a sign analysis on it. We're going to be able to tell from that sign analysis where the function is increasing and decreasing and write down those intervals. We can look at that sign analysis and find the critical numbers, the places where this original function changes, whether it's increasing or decreasing. We can look at those changes, the critical numbers, and know which are relative maximums or minimums from that sign analysis. Then we're going to look at the second derivative and do sign analysis on it. From that sign analysis, we'll be able to tell whether the function is concave up or concave down on the intervals. We will also be able to tell from that sign analysis the points of inflection, the points where the concavity of that original function changes. We'll be able to find the x and the y-intercepts of that function. We'll be able to find the equations of any and all asymptotes on the function. Then, with all that information, we will sketch it, and I definitely recommend a check on Desmos. And then, some smart aleck teacher, I'm assuming, actually I know Mr. Thomas about 8 or 9 years ago when he made this. K is the letter after J, and L is the letter that is on your forehead. If you wrote down K, funny guy. Okay, so those steps A to J. Now, if we have a look briefly, we're not going to do these easy examples. These examples you did last year, and I think most of you mastered them. You can tell from here that there's a 0 at 2, right? From here you can tell there's a 0 at -3. That 0, you can tell what happens at it from the multiplicity. This is a multiplicity that's odd, meaning at that 0 the graph is going to be tangent to and crossing, right? Whoopsie. Multiplicity 1 here, what happens then? I can tell you're saying it out loud, I just can't hear you. It crosses, right? What else can we tell? If we would multiply the leading coefficient, we would have x cubed multiplied by x. The leading coefficient would be 1x to the power of 4, which tells me what? It's positive, right? And it's even, so it's going to go, if we're talking quadrants, from here to here, right? Quadrant 2 to 3. What else? We could multiply the constant terms. -2 cubed would be -8 multiplied by 3, which is -24. We could know that from looking at that the y-intercept would be -24 when it went through. So, geez, if I would sketch this quickly, -3 is here and 2 is here. It starts up here. It crosses straight across at -3 and goes like that, and it's tangent 2 and crosses there like that. Okay, so we know how to do this already. Why do a polynomial question? Well, we could do that one. There's a good one too. Let's do this number 3 together, and then we'll wrap it up for the year. All right, looking originally right at this function, we can tell that its vertical asymptotes are going to happen at x equaling plus and -3. Okay, that's right from the denominator. We're just right off the bat stating the domain, and it can't be positive or negative 3. The first step is to find the first derivative of this rational function. You can see we're going to use the quotient rule. I would like you to go ahead and do that, and I'll pause it and do the work on the screen, and we can compare when you are done. After that, we will do a sign analysis. Alright, here's what I got for the first derivative, negative 16x over x squared minus 9 squared. And we're going to put that into the sign analysis now. Alright, so the sign analysis is like this, and we can see there that the derivative of f of x is positive on the left here up until 0, and then negative on the right, meaning that the original function f of x is increasing here on this interval and decreasing on this interval. That's the answer to B. C, we're looking at the critical numbers, the exact spot where the graph changes from increasing to decreasing, and that happens right here at the 0 of the derivative. And so we know that the critical point happens at x equals 0. When we put a 0 into the function, we result this y. So here's the critical point. Okay, we were looking now, oh yeah, the relative extreme points. Now we know when this is D, the relative extremes. We know when we move from increasing, something going up, to something going down, okay, we know that there will be a relative max at that critical point at 0,1/9. Okay, we know that from the first derivative test. Okay, moving on. E is asking us to find the second derivative, so I'm going to pause here, or you're going to pause, and figure out the second derivative using the first derivative again, the quotient rule. Okay, here's the result with the second derivative. Hopefully you got the same. Now I'm going to set up the sign analysis for the second derivative with these factors. So here's the result of that sign analysis, and now we can tell that the original function f of x is going to be, this is negative, so that will be concave down. Here, f of x will be concave up, being that the second derivative is positive, and here f of x will be concave up. So those intervals we can write down. Concave up is on negative infinity all the way to negative 3, and or the other one, 3 all the way to positive infinity, and concave down between the two from negative 3, open interval, remember, all the way to positive 3. Excellent. Okay, so we're looking for points of inflection now, and then the intercepts. Points of inflection come from the zeros of the second derivative. Now we notice in looking here there are no zeros, so there must be no spots on the graph where there's a point where it turns from concave up to concave down, or vice versa. Okay, there's no changes in concavity on the graph. So here we just say, whoops, I'll use blue, none. No points of inflection. And H, the intercepts. Okay, if we put a 0 in for x, we can find the y-intercept. And if we put a 0 in for y, we can find the x-intercept. So go ahead and do that. Okay, so it looks like we've got a y-intercept of at 1/9 on the y-axis, and an x-intercepts, or two of them, at 1 and -1. Lastly, we're asked to find the asymptotes, and if we look back at the original function, you can scroll up if you need to, we have a degree of 2 divided by a degree of 2. So when we find the degrees are equal, then we have an asymptote at the ratio of their leading coefficients. which in this case is 1 over 1. So we have, these are horizontal by the way, horizontal asymptote at y equals 1 because their degrees are equal. And vertical asymptotes, we've already talked about that. That was the restrictions right in the domain off the start. That was at x equals positive and negative 3. Okay, now let's see if we can sketch it. You can look back and forth with your information above if you want. And there's a graph paper on page 28 if you want, or use the top of page 27. That would make more sense. Okay, so let's go through this. The intercepts, we can write those on. That's happening at 1 and negative 1, and also at 1.9. No, sorry, 1/9. I guess even smaller, right there. We said we have a vertical asymptotes at negative 3. Remember, this is a sketch, so I'm not being too precise, obviously, for my messy asymptotes. Put arrows on. Okay, they don't stop at the end of your graph. They go on forever in both directions. Okay, what else did we know? Now, in between, let's look at our sign analysis. In between these asymptotes, and they're on both of the sign analysis, we have the function. If we look at the first derivative, we have the function increasing until 0, which makes sense. I'm assuming it goes through there. And then at exactly 0, right here at this top point, at the y-intercept, it starts decreasing, which would confirm that. If we look at the second derivative, between these asymptotes, it's supposed to be concave down, which that also confirms. So let's go ahead and write this in the sketch. Okay. Now, on the other sides of these asymptotes, if we look at the first derivative, we know that the function must be increasing. So somehow it has to come and go up here. Okay? Oh, what I'm forgetting is we haven't written in the horizontal asymptote, which was at 1. That was supposed to be here. So that also gives us a little hint. Okay, now we can look at this. It's going to be increasing, so either here increasing, it doesn't make sense because the graph's not just going to stop. It's going to go infinitely close to the asymptotes. So I'm assuming it's up here increasing. Let's see what the concavity looks like with the second derivative. It's supposed to be concave up, which does confirm that here. So let's go and sketch this in. Now, of course, we could figure out a point that it goes through here. If we put in a y of -4, we could figure out exactly where that would go, but we'll just do a sketch. Often now graphs mirror each other, so I'm assuming this goes here. Let's just look at that. First derivative says it should be decreasing. That would be true. And second derivative says it's supposed to be concave up. So yes, that would also be true. So there's a rough sketch of it. Now I didn't go and get the Desmos version, but you can have a look at that if you want. Okay, proceed to the summative assessment for this unit.